All right, so guys, today we are talking about the photoelectric effect and quantum theory. Okay, photoelectric effect and quantum theory. All right, basically, here's the idea. Up until right now, what we've done so far is we've said that the speed of light can be found by taking the wavelength and multiplying by the frequency. We know that all electromagnetic spectrum move at the same speed, and that speed has a value of 3.00 times 10 to the, I'm going to say 8th meters per second. Although you guys also know it's 17 nanometers. Okay. Ultimately, what we understand is that light moves as a wave, because only waves have wavelengths, okay? But, oh my goodness, no, we're going to hurt your brains here. The wave model of light doesn't explain how it is that different things can give off light. Okay, it doesn't explain the Blackbody effect, which is the effect of when something's really hot, it glows. You guys have seen that happen before, right?
How is that called the Blackbody?
I don't know why it's called the Blackbody effect. It just is. It's a because you're talking about like a piece of iron that if you heat up really, really hot, it eventually gives off light. So originally it gave off no light. Eventually it gives off light. So a black body, like, you know, dark body. That's my logic of why they call it that.
I think I'll just think about it again for.
Okay. The spectrum doesn't, I'm sorry, the wave model of light also doesn't talk about why electrons are emitted when light hits a piece of metal. That's called the photoelectric effect. And it also isn't going to explain the emission spectra of light, why it is that Vegas makes so much money off those lights that they have out in front, or the dentist who, no, not the dentist, the stores that have the open signs that glow.
I hope that's not a dentist.
Okay. The barber shop, right? Okay. So a guy named Louis de Broglie, he's not from broccoli. He is de Broglie. He is from Broglie. All right. At any rate, he figures out that when light travels through space, it behaves like a wave. He knows this. Okay. He also notices that when light interacts with matter, it behaves like a stream of particles, but he can't figure out how to prove that, how to deal with that. Okay. Max Planck comes across and he says, okay, I'm going to try and come up. All right. So Planck comes across and he realizes, he postulates that energy can either be released or absorbed by an object in discrete amounts, discrete packets of some size. Yes, write this down. This is called, the singular is quanta, the plural is quantum. Okay, so if you want to talk about lots of packets, you say quantum. If you talk about in one individual packet, you say quanta. Okay, so quantum simply is talking about a fixed amount. So when we talk about quantum mechanics, we're talking about the mechanics of energy at very fixed amounts, at the very small fixed amounts at this quantum level. Okay, so Planck is the first guy to talk about quantum things. Quantum, as far as he's concerned, is the smallest quantity of energy that can be emitted or absorbed as electromagnetic radiation. So he says that electromagnetic radiation has to come in certain size pieces, quanta. Whoops. So, to continue with Planck's quantum theory, not only does he describe that light, that energy coming from matter is going to be in packets like Skittles, but he comes up with an equation. He says that the amount of energy, E, is going to be equal to H times nu.
H is 6.6262
Okay.
times 10.
Where energy is measured in joules, frequency is measured in hertz, just like we know, and H is going to be Planck's constant, which you guys read about, and I know you highlighted or underlined it. 6.626 times 10 to the negative 34th joule seconds.
Isn't there two? It's like 6.6262.
Yeah, if you want to throw the other 2 in there at the end, you can. I know your reading had it in there. I think our current textbook does not have the second 2 in there. It's not going to hurt your answers at all, whether you include it or not include it. Okay. This, you'll notice that it is for a single quantum, or a single photon is another way to say that. So this is not a mole's worth of photons. This is for a single photon. So if you see a single photon, you are absorbing 6.626 times 10 to the negative 34th joule seconds times whatever the frequency of the light is of energy. Okay, so far, these are our only equations. C equals lambda nu and E equals h nu. You can solve absolutely everything with only these 2 equations, but we can complicate things. We can say, hey, I could rewrite this equation to solve it for nu. I could say that nu is C over lambda. Then I could take this equation and I could say, okay, it has nu in it. I could say that the energy is equal to h c over lambda. Basically, I'm taking this nu. Nu is equal to c over lambda, right? So I'm just replacing the nu with c over lambda. Okay, so this is another equation that is useful in finding the energy. Sometimes we're given the frequency and we'd use the top equation. Sometimes we're given the wavelength and we can use this bottom equation.
So those are both quadratic equations?
Okay, so we basically, what we've got here is we've got 3 equations that are possible to use from, that will be given to you on the test.
What is this value in
Okay, we're not quite there yet, Matt. I want to make sure we're comfortable with the equations that we've set up.
That's how I find.
So we've got this other question here that's pointed out. There are actually 2 versions of H. I'm going to show you how to get the second version of H. It turns out that this is only good for a single photon, right? How often do you come across 1 photon of light in your life? Not very often, right? You'd see 1 tiny, right? There are lots and lots of photons right now in the room. So it's more useful to talk about it in terms of moles. But if you talk about it in moles of photons, then you need to talk about it in kilojoules rather than just joules, because you're talking about so many photons. So here's what we do. We take the 6.626 times 10 to the negative 34th, sorry, joules times seconds, and we'll multiply it by a mole, 6.022 times 10 to the 23rd. Okay. That's going to come up with a pretty big number, but here's the thing. We don't want it in joules per mole. We want it in kilojoules per mole. How do we convert from joules to kilojoules?
Times 2. I feel like it's
Okay. So
times
we're also going to divide the whole thing by 1,000.
swag.
Okay. What this is going to do is this is going to give us units of kilojoules, seconds per mole, and the value of this number, yeah, 3.989 times 10 to the negative 13th kilojoule seconds per mole.
That's what everything is for every single
Okay.
photon?
Nope.
For what?
Okay. So these are the 2 versions of H.
Kilojoule seconds?
Kilojoule seconds per mole.
How would you know where to use this?
Okay. Well, because you'll look at the question, what they give you. Since the question gave us a wavelength, we want to use the energy calculation that has wavelength in it. Okay. If they give me a frequency, I would have used this other one, E equals h nu. Okay. Ooh. This is for how many photons?
Well, just one.
One.
A photon. So I'm going to need to replace my H with 6.6262, just for Brian, times 10 to the negative 34th joules times seconds. Multiply that by C, which is 3.00 times 10. Should I use meters or nanometers? Nanometers. So 17th nanometers per second. Brian, why'd you say nanometers?
Because there's nanometers in the question.
Right, nanometers in the question. And then what goes on the bottom here? 589 nanometers. Okay. Hey, if we want to use these units properly, we should cross out the things that cancel, right? Nanometers cancel with nanometers. Per second cancels out with seconds. What units do I wind up with? Joules. Okay. So what we wind up coming up with is that a single photon of light of wavelength 589 comes out to be about 3.37 times 10 to the negative 53rd joules. An extremely tiny amount of energy. Okay, so yeah, I had negative 53rd. It's actually negative 19th. Sorry about that.
A little bit less.
It's still, now you got negative 17th? Okay, all right, negative 19th. Negative 19th sounds. If I've got to do a Molesworth of photons, I'm going to use the same equation. I'm still going to use E equals hc over wavelength. The problem is that h has a different value since I've got a mole's worth of photons. Okay. Now it has a value of 3.989 times 10 to the negative 34th kilojoule seconds per mole. I'm using the same exact equations. So the other thing, C on the top is still going to be 3.00 times 10 to the 17th nanometers per second. Wavelength should still be 589 nanometers. Nanometers and nanometers will still cancel. Seconds and per second will still cancel.
Wait, I think she's right about this point.
Okay, so yeah, you're right. I miscopied. Negative 13th here. Okay. It's going to get us a slightly different answer. So I'm getting 203.17, and that should be in kilojoules per mole. Okay. So we do have to talk about one or two more things real quickly here. Okay. Planck's ideas. Don't write anything down, guys. I'll leave this slide up here. Planck's ideas were just that. They were hypotheses. They had no theory whatsoever. Oh, they were theory. They were not proof. Okay? So they needed someone to come up with a proof for this, and Einstein actually came up with the idea. All right? It's called the photoelectric effect, and the idea behind it is this. He took a piece of metal, potassium, all right? He hooked up the piece of potassium to a voltmeter so he could measure voltage. He put it in a dark room. He gets no voltage in a dark room. He pulls out a red light and shines a red light. Red light has the least amount of energy, remember. And he shines this red light of 700 nanometers on this piece of potassium. He gets no results from his voltmeter. Nothing happens. Okay. He then says, okay, let's use some higher energy light. Let's use something like green. So he takes light of 550 nanometers, which is green. He points that at his piece of potassium in the dark room, and this time his voltmeter changes. He gets a voltage. He's able to calculate that the electrons actually were moving around. Okay? He says, okay, this is a proof for Planck, but it's only a proof for Planck if higher energy light does more. So he takes the 400 nanometer light, purple, he points it at the same piece of potassium in the same dark room, and since it's higher energy, it releases the electrons at a higher speed. Okay, so the photoelectric effect is two things. It is A, proof that Max Planck was right about the quantum, and B, it was a really, really great find, because where is this in use today? You all, well, most of you guys have one on your desk right now.
Phone.
Not a phone.
Calculator.
It is in your calculadora. What portion of your calculadora has a device that allows light to hit it and lets electrons flow? Your solar panel.
Well, the
Okay.
two things that
So basically, Einstein has made a solar panel.
prove that
All right. Thus, yay! At the end of this lecture, we find out that light has two natures. It is both a wave and a particle. It just depends on how you want to look at it at that moment in time and what you're measuring. Okay?